Hey there everyone, it's your main math teacher, Mr. Boyden, back at it again today. We're talking about separable differential equations and slope fields. The easiest way to get started thinking about this is to think about flowing water. And so we're going to try to answer the question below. If we drop a rubber ducky off the Narrows Bridge, how can we know where it's going to go? Where is it going to float to? Where is it going to land on the beach? Will it land on the beach or will it get stuck in a whirlpool? And one way we can start to think about that is with a slope field. And so I'll give you an example in here. Let's say the water is flowing inward. It's an inward tide. And here's our Tacoma Narrows Bridge right here. And so what a slope field will tell us is the direction that the water is flowing. And so we can see here the water's flowing. I'm sort of making this up as I go, but it's just an example to illustrate. The water kind of flows around the corner, and some of the water flows here and is forced to go one way or the other. So we get water that flows down this direction. The water that flows up here, some of it will flow into this passage, some will flow here and end up going that way or that way and coming around, continuing around these corners. Some of it will flow down this direction through this little channel down toward Chambers Bay and down in here by University Place. And some of it will flow up around Fox Island, and some of it will continue to flow south. So the idea of this then, with asking what happens to our little ducky, if little ducky gets dropped right here, all we do is we can track the direction of each of these little lines, and we can see where the ducky goes. So here's ducky. I'm following the little lines. Looks like ducky goes around into here somewhere. Well, what if we move ducky over and dropped him in the middle? Well, then little ducky flows like this. And what if little ducky went all the way over on the right? Well, little ducky's just going to flow, go with the flow, go with the lines, and little ducky's going to end up down in Olympia somewhere, or down in Steilacoom somewhere. So where we choose to drop the duck matters, and a slope field illustrates how that works. Now, another example of that we can use is this. And so in this graphic, we have the wind currents around the whole globe. And so this is a little bit more dynamic than what we're doing in AP Calculus, but you can see how you can tell the direction from this graphic. You can tell the direction that the wind is going. In this one, it's dynamic, so you can actually get the speed, and you can see how it's looping around in here, and you've got some sort of a circular flow there. Why would we care about this? Well, you'd care about this if you were flying an airplane from New York to London, because you're going to have to fly through this stuff. And maybe if you know the air currents, you can take the most efficient route possible or something like that. Okay, so in order to get into more of the math of this, I want to start with a concept that we already know, implicit derivatives, and I want to connect that to what we're doing because we're essentially just going to do that in reverse today. So let's take a look at our prompt here. We're given x squared plus y squared equals 25, and we are asked to find the derivative. So let's do that. X squared is going to turn into 2x, and y is going to turn into 2y dy dx. And 25 is a constant, so it goes away. Okay, and we've written down sort of our differential equation, and we're asked here to solve it for dy dx. And so I'm going to do a little mental math on that, and I'm going to get dy dx equals negative x over y. Okay, and so that is a differential equation. That actually is a separable differential equation. Later we're going to learn how we could work that backward to actually get x squared plus y squared equals 25. Before we dig into all the math of that, though, I want to take a minute and look at how to visualize them, because that's what a slope field is. A slope field is the visual that accompanies a differential equation. And so let's take a look at these examples that we have here. Oh, looks like my dogs are barking. So that tends to happen when I record these at home. So let's take a look at our slope field here on the left. Notice that is the exact same differential equation that we had just a minute ago. And so what I'm going to do is I'm going to start picking points, and I'm going to plug in the x and the y values. And I want to start right here. And right there, I have 1, 1. If I plug those in, I get a slope of negative 1. And so what I'm going to do is put in a dash that has an approximate slope of negative 1. It's not going to be exact, but it is going to be able to give me a good idea of the behavior of the function. I'm going to come up here next. That looks like it is 2, 2, so plug that in right here, and we get negative 1 again. And I'm going to kind of pick out all the easy ones. These are all the places where the slope is negative 1. And then I'm going to try the other diagonal. So I'm talking like right there. So 1, negative 1, plug that in, and we get a slope of positive 1. Same thing here, positive 1. Same thing here, plugging in the coordinates of this point, positive 1, and right here, positive 1. Now notice, there's not a lot of precision to this. I mean, I'm representing a positive slope, but I don't have the exact numbers or anything like that. And I'm just looking for the easiest numbers. I think this point is going to be pretty easy to do next because we know the x value is 0. So that's 0 divided by 1, which is 0. Same thing here, x value is 0, x value is 0, x value is 0. What about at the origin? At the origin, I get 0 divided by 0. That's an indeterminate form, so I'm going to go ahead and leave that one alone right now, and I'm going to work on filling in some of these other points for a minute. So I'm going to come out here, and it looks like I have an x value of 2, y value of 1, so that's a slope of negative 2. Now that speaks to the lack of precision, because right to the left of that, we had a slope of negative 1. All I'm showing here is that this is a little bit steeper. Let's go up. This looks like we have an x value of 1, y value of 2, so that's negative 1/2. Coming over to the left, we get positive 1/2. Looks like we get 2 right here. And let's go down into the quadrants that are below the axis, quadrants 3 and 4. I'm going to come over to here. Looks like I am 2 to the right and 1 down, so that would be a slope of positive 2. Looks like I have a slope of positive 1/2 right here. Looks like we have a slope of negative 1/2 here and of negative 2 right there. Now, I want to deal with the points that are about the origin, or excuse me, that are on the y-axis. Nope, the x-axis, sorry. Third time's a charm, there we go. So I'm talking about like this point right here. Now, when I plug those in, I get negative 1 divided by 0. And so we have to think what kind of a slope would give a 0 in the denominator, and that's going to be a vertical slope. Okay, so I'm going to put verticals in on all of those. Why am I not putting one at the origin? Well, because at the origin, it's 0 divided by 0. When I had a number divided by 0, like 1 divided by 0, that's infinite. But 0 divided by 0 is indeterminate. I have no idea what it is. So now, just from looking at what I've graphed so far, we should be able to tell that this makes sort of a circular type of pattern. And that actually makes perfect sense. Because if we look at where this differential equation came from, it came from something that was a circle. And that circle is right up here. So remember, we learned about this in pre-calculus. This right here is a circle with a radius of 5. X squared plus y squared equals r squared. That's the equation of a circle. So that kind of makes sense. And here's the connection. When we have to plot a point or a solution curve through a point, first of all, let's find where that point is, negative 1, negative 2. What we're doing is basically dropping that rubber ducky over the bridge. And we're saying, okay, now if this is a water current, where would this flow? To me, it looks like it's going to flow right around something like this. It's not exact, but it doesn't have to be. This is just a visual representation of a concept. So let's try the one on the right now. You may want to pause the video and try it yourself. Let's see. So when I go over here, first thing I notice is the x value has nothing to do with the slope. Only the y value is affecting the slope. Why am I saying slope? Because that's a derivative, and derivatives are slopes. So let's do this. When I am on the axis, and I'm talking about the x-axis, so here, 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 and here, it looks like the y value is 0, which means the slope is 0. So I'll fill all those in, even the origin this time, because it has nothing to do with x. Okay, so all those are in. I've got a bunch of those horizontal dashes in there. When I come up 1 and I plug in a 1 in for y, I get a slope of 2. 2, 2, 2, 2, 2. If I come up here where the y value is 2, now I get a slope of 4. And so I'm really exaggerating how steep these are, because all that AP is looking for, they want to see that this is not as steep as that. That's how they grade them. Okay, let's come down into quadrants 3 and 4, and it looks like down here when you plug in a negative 1, you're going to get a slope of negative 2. And when you plug in those points with y values of negative 2, you get a negative 4. So I need to demonstrate that these are steeper than where the y value was negative 1. Now let's deal with this prompt. Negative 1, negative 2, sketch a solution curve through that point. And that looks like it's something like that probably. Probably something, I'm thinking that right along here is probably a horizontal asymptote. So there we go. Now that goes back to, it really matters where we drop the ducky or where we start our solution curve at. If I had started my solution curve here, I'm going to end up with a different curve. It goes into different quadrants, it goes in a different direction, it probably does something like that. Okay, so that makes a real big difference. And that is something that occasionally we will be asked to sketch. let's get in now to the actual nuts and bolts of how to solve a differential equation. So we're given one here. This is a two-part question. This is a really normal type of question that AP will ask. So let's get into it. First thing we want to do, I'm going to bring this down and rewrite it down in space here so we can operate a little bit. So dy dx equals 3xy squared. Okay, now here's what they mean by separable. We have a situation where we have x and y on both sides of the equation. Wouldn't it be nice if we could take this multivariate situation and turn it into two different questions, each of which only had one variable? Well, of course that would be nice, and that's exactly what we're going to try to do. So for the first time, we're going to actually break this little derivative symbol apart. I'm going to multiply both sides by dx, and so the dx is over here with the x, and then I'm going to divide both sides by y squared, and so the y's are together. Now once we do that, here's what we have. We end up with dy, and I'm going to rewrite it in a way that is easy to deal with. So instead of writing it over y squared, I'm going to write y to the negative second power. And when I'm going to come over here, I'm going to have 3x dx. And so here is how this technique is useful. See how we have this dy and dx at the end? That looks a lot like an integral, right? So I'm going to slap those on there. And this goes back to that idea with algebra. You can do basically anything you want to an equation as long as you do the equivalent thing on both sides of the equation. And so all I'm going to do, I'm going to integrate both sides. So let's give it a shot. Okay, dealing with the right side, that's not too bad. Looks like we get 3x squared over 2 plus c. Don't forget your plus c. On the right side, we get y to the negative 1 with a little minus right there. Okay, and we got to keep going with our algebra, but this is the basic gist of how they go. So let me extend my screen just a touch here. I'm going to rewrite this as negative 1 over y, and I'm going to say that equals 3x squared over 2 plus c. Now, one of the things that we should talk about is why we only wrote plus c once, because some people really want to write plus c here as well. And that runs into a little bit of an issue, because we had this constant of integration that came from here and this constant of integration that came from here. And the first issue with that is when you write both of them and call them c, it's sort of implying that they're the same value. And we have no information that leads us to believe that. So we don't know that they're the same value. So we have to be careful with that. Then some people say, well, wait a minute, why don't you just call this k then, or some other constant? We totally can. There's no reason why we couldn't, but it's pretty excessive. Because what we're going to do is we would then subtract k over here, and then what would c minus k be? Well, I don't know. It would be a number. And what symbol would we use to represent a number? We would use c. So regardless, you're going to end up with plus c over here. And so it's not worth going through all of the steps to deal with that plus k. So I'm going to get rid of that right now. Let's make that go away. And we were given some more information in this question. We were asked to give the general solution. I've got that right here, actually. So that is the general solution. We were also asked for the particular solution for the point 1, comma 2. And so I'm going to deal with that now. 1, comma 2. And what that's going to allow us to do is find that c. So let's plug in some numbers and see what we get. I get negative 1/2 equals 3 times 1 squared over 2 plus c. And then what I've got negative 1/2 equals 3/2 plus c. And so that tells me that c is negative 4/2, or c is negative 2. And so when they ask for the particular solution, what they're asking us for, they're asking us to take the general solution and rewrite it with our knowledge of c. So I'm going to put a little g here. That's the general solution. We're going to bring that down to the right, and now we're going to try to write out the particular solution. And so I've got negative 1 over y equals 3x squared over 2 minus 2. So what I'm going to do is I'm going to rewrite this. I'm going to leave the negative 1 and the y. But over here, I'm going to get 3x squared minus 4 over 2. Notice that's 4 over 2, which is just 2. Then I'm going to flip both sides. It's like you can do something on one side, do it on the other. I'm going to flip the left side, flip the right. And so what I get when I do that is negative y equals 2 over 3x squared minus 4. Let me separate my work here so it's not confusing. And then I want to get rid of that minus, so all I'm going to do is I'm just going to transfer that over to the other side here. And I need to erase the one on the left. And that now is the particular solution that they asked for. I'm going to put PS there for particular solution. And that is the same exact idea as where are we dropping the ducky? What would the curve look like? Now before we drew it, this time we actually found the equation of that curve. Let's look at a couple more examples. Okay, here's our second one. Now, if you're feeling like you're ready for it, I suggest that you pause the video and try it on your own. You may have a really good shot at doing this, and then if you want to play it and see how you did, that'd be a cool thing. So with this one, I'm going to go right into the steps. I'm noticing that dx is going to need to come up, and then dx and x will be together. I'm going to want to move this y squared up over here, so I'll be multiplying by both of those. And then what I'll have is y squared dy equals x squared dx. Sweet. Let's integrate over both sides. And so we get y cubed over 3 equals x cubed over 3 plus c. And they say solve the differential equation. Check. There's our answer to part A. We've done that. Now, the part B here is the exact same thing as the previous example. It's just in different language. So I'm doing that on purpose to show you different ways this question might be asked. They want the solution of this equation that satisfies the initial condition or the boundary condition, y of 0 equals 2. Now, they're telling us that's the point 0, comma 2. Okay, so that's the same information as before. So let's plug that in and see what we get. Okay, on the left-hand side, I get 8/3. On the right-hand side, it zeroes out, and hey, automatically I already have c. That's great. So let's plug c back in and see what we get. I've got y cubed over 3 equals x cubed over 3 plus 8 over 3. Cool. Well, multiplying both sides by 3, all of that cancels out, so that's cool. I want this to be solved for y, and so I'm going to cube root both sides of this, and then that actually, right there, gives me my solution. And so what I've got is y equals cube root of x cubed plus 8. And that now is my particular solution given my solution point or my initial condition. Third example, and this one starts to look a little bit more exciting, so let's get right into it. Right away, the first challenge I'm trying to show you is that this is going to say y squared. It's going to be a little easier if we start out by rewriting this as dy dx. Otherwise, it's not going to be obvious to us that it's separable. Now, y prime just means the derivative, and dy dx means derivative. So that's why that's going to be all right. Now let's rewrite the right side. 6x squared over 2y plus cosine y. Okay, and let's do our separation of the variables. So dx is going to come up here. All of this stuff with the y's in it is going to come up here. And so what I get is 2y plus cosine of y dy equals 6x squared dx. And now we can integrate that. So let's do it. Okay, on the left-hand side, that 2y, so we're raising the power of y to 2, and so we get y squared plus sine of y equals, okay, remember that 2 is going to become a 3, and then we're dividing by the 3, so that would be 2x cubed plus c. And that actually satisfies the question we were asked, because we were asked to solve the equation, okay? And we've done that. We have now presented something in terms of x and y. We started with a derivative, we've worked backward and presented something in terms of x and y. So we've actually satisfied the prompt. Now let's take a look at a typical free response question from an AP exam. We're given a differential equation, And the first thing that they're going to ask us is to sketch a slope field. This is a really standard AP test question. And so we're going to go down here and let's try to fill in our slope field. I'm going to start right here. And remember, all we're doing is we're plugging values into this equation right here. And so x is 1, y is 1. That means the slope is 2 over 1. I'm going to come down here. Looks like x is 1 and y is 0. So I get 1 over 1 or a slope of 1. Come down here where y is negative, and that zeroes out the numerator. So I have a 0 slope. Coming out to here, y is 0, x is 2. So that gives me a slope of 1/2. Okay, let's come up to here where we get a negative 1 for x and a positive 1 for y. So the numerator is going to say 2, and then my denominator is a negative 1, so that gives me a negative 2 slope. There's some symmetry across the axis here. Coming right to this point, looks like my x value is negative 1, so I've got a negative 1 in the denominator. I've got a positive 1 in the numerator. That gives me a slope of negative 1. Hey, more symmetry. Look at that. And I'm going to come down here, and I get negative 1 for both numerator and denominator, and so that gives me a 0 overall. And so then we're going to come back up to here, and I plug in a negative 2 for x, and so I get 1 over negative 2, or negative 1/2. And then let's deal with the stuff on the axis. So x is 0, and y is 1. So I get 2 over 0. Looks like maybe that's vertical, and I plug in a 0 right here. So 0, 0, I get 1 over 0, and that's vertical. And then down here at the bottom, I've got a negative 1 that I'm plugging in. So that's 0 over 0, so it's undefined right there. So we don't want to write anything at all in that location. Okay, so that's part A. Now let's go to part B. And so I'm going to take this equation, and we are asked to find the particular solution given our initial condition. And so we can definitely do that. So I'm going to buy myself a little more space here, and I'm going to start separating right away. And so what I get is dy over 1 plus y equals dx over x. And for a lot of people at first, that can be just a little bit confusing. So let's rewrite this in a way that's a little bit easier to see. One over 1 plus y dy equals 1 over x dx. And one of the reasons I like to write it that way, for myself, it makes it a little bit easier for me to see that I'm now dealing with logarithms. So when I integrate that, I'm able to much more easily recognize the form on the right side. That's going to be natural log absolute value of x plus c. And it also gives me a way of thinking about what would have led to 1 over 1 plus y as a derivative. Now, it's definitely a natural logarithm, and it's going to have a 1 plus y in there. And if you're having trouble thinking about that, ask yourself, how would you take a derivative of natural log of 1 plus y? You'd find the derivative of the inside of the function, the 1 plus y, and that would be 1, and that would give you the numerator, and you would write 1 plus y on the bottom. So that matches exactly. And so now we have our general solution. I'm going to go back up because I want to see what my points were that I'm plugging in. I'm talking about this right here, negative 1, 1. And I'm going to plug those in now and see what I get. And I'm going to do this sort of mental math style. So on the left, we get natural log of 2 equals the natural log of 1. Remember, the absolute value makes it positive, and natural log of 1 is 0. So that just told me right there what c is. And so now I'm ready to go about the business of writing down my particular solution, which is what they asked for. And so here we go. I get natural log of 1 plus y equals natural log absolute value of x plus natural log of 2. And they're going to want us to simplify that down and solve that for y. And so that's going to take a little bit of work. Now, it would be really nice if I could raise both sides to e and make those natural logs go away. I can't right now because I've got a sum over here. But if we remember that when you have a sum of logs with a common base, there's a way we can rewrite that. And so this is going to turn into, I'm just rewriting the left side, but the right side is going to turn into natural log of 2x. And that now just got a whole lot easier because now we can raise both sides as exponents on e, and the natural logs will cancel out, so we get 1 plus y equals 2x. And then I can get rid of these absolute value bars by doing a plus and minus. So I get 1 plus y equals, those are still there, plus or minus 2x. We'll subtract 1 on both sides. And so now I've got an answer. We've got to do just a little bit more interpretation though, because not both the plus and the minus will probably spit out this point right here. And so we need to go back down and ask ourselves, if we plugged in a negative 1, would we get a positive 1 out? So if I plugged in a negative 1 right here, so 2 times negative 1 minus 1 equals 1, we have to figure out, is it the positive or negative version of this that we need? Now, as that sits, that reads as 2 times negative 1, which is negative 2, minus 1 equals negative 3. And so that doesn't work. But if I put the little minus there, now I have negative 2 times negative 1, which is 2. 2 minus 1 is 1. So what this indicates is that I need the negative version for my answer. So we had to interpret this and figure out whether the plus or the minus was correct. And it turns out that it is the negative version. So negative 2x minus 1 is what I needed. And there is my particular solution. Okay, so we've run through about 4 examples now. That's probably enough to get you going on the practice. Hope you enjoyed this video, and I hope it was helpful. And good luck. We'll see you next time.